Okay, so basically, we're just going to use some of your exponent properties today with a couple more things. So a quick refresher, if you're multiplying terms, then you add their exponents together. If you have like powers raised to another power, then you're going to multiply the exponents instead. So on this one, you'd end up with 256 times x to the 12th. What we're looking at today is basically a special number called e. It's an irrational number, kind of like pi is 3.14. E is just approximately 2.71. So if you're simplifying powers of e, you just use your exponent properties like you would with any other variable. So if you're multiplying all these together, you'd add your exponents. 9 and 6 are like terms, so you could make it 15. 5x can't be combined, and you're good. If you're simplifying this one, you would divide 60 by 12, which gives you 5. And then if you have powers top and bottom of your fraction, we subtract them. Like if it's x to the third over x squared, you subtract 3 minus 2 and get 1. Here you're going to subtract top power minus bottom power, which is just 8 minus x. So really it's just using things you already know. E is a number, not a variable. It works the same way though. If I break down this radical, I could turn 16 into 4 and 4. I could take it all the way into 2's, but I'm not going to. I'm listing out how many e's I have. It's a square root, so for every 2 factors, you get to bring one outside. So you end up with square root of 16 gives you 4, and then 3 factors of e gives you 4e to the third. Here you have some expression being raised to the third power. So I'm going to write it out with everything's power being multiplied by 3. If you actually do that multiplication, you have negative 1,000 for your negative 10 to the third, and then e to the negative 15x. Because that's a negative exponent on my e, I'm just going to go ahead and make it in the denominator as e to the positive 15x. It's kind of a toss-up if you have to do that on e's, but I'm going to go ahead and do that. Now I'm going to give... Okay, so those are exact values for your expression. You can use a calculator to approximate powers of e, just like if it's 2 to the 5th, you can make it 32. You can do like e to the 6th and get an approximate value for it if there's no variables in there. So I'm just using the scientific calculator that's on your iPad. You could do e to the 6th power, which is just approximately 403. I'm going to round to 3 decimal places. You could also use a regular calculator if you have one or prefer one, but I'm just going to jot that down right there. And that's all e to the 6th power is approximately 403.429. E to the negative 0.28, you can again just use a calculator to approximate, which is approximately 0.756. Let me show you what the buttons look like on a regular calculator. So you'd hit your second key, at least on mine, and then it's on the capital LN button. Pops up e to the, and it'll give you an opening parentheses, and then just type your power and be sure to close your parentheses. These can be growth or decay, just like the exponential functions that we've been talking about. It depends on whether or not your power on e is positive or negative. Oh, also, by the way, e is called Euler's constant, which I hadn't mentioned up till now, but that's what e is called, is Euler's constant. So something like 2 times e to the 3x, where your power is greater than 0, would be growth. If it's the like negative 2x, 3x power, it would be decay. So on this one, it's the 1/2 x power, which is greater than 0, so that would be exponential growth. You can always think of e as like 2.71 also, if it helps you. Where if we talked about like 2 to the x power, since 2 was greater than 1, it was exponential growth. This is the same idea. So you can always turn that back into a number and think about it. If you have e to the negative 3x, that's going to be exponential decay. The reason why it's really exponential decay is because if you think about that as a negative exponent and you have 1 over 2.71, then the base of your exponential function is a number that's less than 1, so that means it's going to be exponential decay. Continuously compounded interest is interest that's basically compounded over and over and over and over and over again, like every instant instead of like once a month or something. The formula looks a little different. You still plug in your initial amount for P, then you have E raised to the power of your interest rate times time. So main thing is make sure you use parentheses around that exponent, especially if you are using a regular calculator, because it won't keep it all up in the exponent like Desmos does. But if you just type that in, you will end up with about $333 after you have your money compounded continuously for those 3 years. Which continuously compounded interest is the kind that's best if someone's paying it to you, because it gets you the most money. College tuition is unfortunately something that can be modeled with an exponential growth model as well. So if you have this model, the amount that college tuition is increasing per year is about 6%. So your rate of change in your exponent is 0.06. If I want to use my tuition cost at Mizzou in the year 2000 to approximate it for the following years, you would just have your initial cost times e to the 0.06 x power. If I want my cost for a specific year, say 2012, which is 12 years after my starting date, I'd plug in 12 for my value of x. Well, I'm really bad at this side-by-side thing. And then if I type in that expression, that should approximate what the tuition was in 2012 if it was increasing at a rate of 6% every year. It is a model. Tuition hasn't increased exactly at 6% every year, but approximately $9,411, which is a little bit more than double what it was in 2000, which is kind of crazy. And our model was fairly close to the actual amount that it was in 2012.